whatever we were discussing in the last class, which is about convergence of random variables. In fact, we looked at two kinds of convergence. What were those?
So one is convergence probability and it is almost surely convergence.
Almost sure and
Convergence in probability.
Convergence in probability, right? So, so let's quickly write the definition of those two. So, xn converges to a random variable x in probability if, what is the condition? So, if probability
modulus
of bad event, that is xn minus x is greater than epsilon, is a bad event, this goes to 0 as n goes to infinity for every epsilon greater than 0, right? So this is what the definition was. And the other one was convergence in almost sure sense, right? So this almost sure sense, this probability of xn converging to x is 1, right? So this is the definition of almost sure. Okay, we saw that almost sure xn converging to x in probability does not imply almost sure. We gave an example. I gave an example in the last class which contradicts this. So the question is, what about the other way? So let's look at xn converging to x. Almost surely, does it imply improbability? I thought I'll not prove this, but maybe I'll just quickly go over the proof. Okay. So what do you mean by xn converging to x in probability? So this means probability that xn converges to x is 1. Now let's look at what do you mean by xn converging to x. That means, so if you have x somewhere here, I'll just look at the numbers. Okay, so let's suppose x is a number and xn is a sequence. What do you mean by x converging to x? So you put a small box around it. Then if you wait for enough time, the sequence will enter this box and will not leave, right? Let's call this box width is epsilon. Well, if this is not the epsilon that you want, you can put a smaller box and then wait for enough time so that the sequence will enter this small box and will stay there forever, and so on. Okay, that's the notion of limit, right? So how do you mathematically write that? So you can say that xn converges to x as follows. You can define it as follows. You give me any box for every epsilon greater than 0. Epsilon will define the box size. Okay, for every epsilon greater than 0, that means there is, give me any box size, there exists, you have to wait for enough time. So what does that mean? There exists a time in epsilon. N epsilon is the stage such that if you look at a n epsilon or xn epsilon plus 1, xn epsilon plus 2, and so on, all these numbers lie within that box. So how do I write that? Such that xn minus x is small less than epsilon. That means lie inside the box. In fact, xn lies inside the box. Okay, of size epsilon. This is what it means, right? So, but this should be true for all n after that, right? So after n epsilon. Is this fine? Understood?
Yes.
Everyone? Okay, this is the definition. So how do you convert this into precise one? So let's consider this an as this set. Okay, so an epsilon as, okay, so xn minus x being less than epsilon. Okay, so let's look at all the sequence n for xn for which xn minus x less than epsilon. This is the sequence, right? Okay, just one second. Okay, okay. So basically, now I have to write this thing, right? So this whole definition. So it says for every epsilon greater than 0. That means for every epsilon greater than 0, there exists a stage beyond which this is less than. That means a n epsilon happens beyond n epsilon plus 1 and so on, right? So that means a n epsilon event happens for all n equal to n epsilon plus 1 to infinity, right? All this happens. But it also says that there exists a stage. That means there is a stage n epsilon, which could be, for example, 0, 1, 2, 3 till infinity. And this event should happen for every epsilon greater than 0. Is that fine?
So what is
Okay.
the union stands for? I didn't understand.
There exists, right? There exists an n. That means what? N equal to 1, n equal to 2, n equal to 3, n equal to 4, and so on, right? One of the for one of the n's, this happens. That's what it means, right?
So the
for
inner
example,
so the inner intersection is for like after in epsilon stage.
every
You,
for every n, it should happen, right? It should be smaller than. It should lie within the room.
okay, the second is for in any. Acha, okay, okay.
There exists. The last one intersection is for every epsilon room size. You give me any room size, it should be true. Okay? Is this fine?
Yes,
So I'll
sir.
just redefine. If you want to be very formal, you can say consider this, where I'll just define n epsilon as the set xn minus x less than epsilon. Okay, this is fine. Now it says for every epsilon greater than 0, right? So you give me any epsilon, right, in the on the real line. There is a natural number slightly smaller and bigger than that, right? I can always find. Do you agree? So this whole set, I can write it in a slightly different fashion. Okay, k equal to 1 to infinity, n epsilon equal to 0 to, or nk in this case, equal to 0 to infinity, n is equal to n epsilon plus 1 to infinity a n epsilon. Okay, so both these equivalent, these sets are equivalent. So I can replace for every epsilon by for every number k, such that nk is less than this. So what is this epsilon? Instead of epsilon, I will have 1 by k. Okay, so that means here I can replace epsilon by 1 by k. For example, if k is very large, that means that this difference should be very small. It's a small room. Okay.
So this should be union, no, in middle. And
Yeah, I'm sorry. You're right. It should be union. Okay. So now I can say probability of xn converging to x as probability that for every k there exists an n epsilon nk, for example, such that for every what? This is n, right? For every n from nk plus 1 to infinity, this should happen. Both are same, right? Is that fine? Is this okay?
yes, sir.
Okay. So now I'll give you the idea. So now what is it that I have to prove? I have to prove that limit n tending to infinity, right? So need to prove that limit n tending to infinity, probability of xn minus x greater than epsilon is 0, right? So I have to prove that an minus, so this is, how do I show that? So xn minus x greater than epsilon is 0. Okay, is that fine? Or less than or equal to epsilon should be 1. That's what we need to prove. You agree? Okay. Okay, so now how do you show that using this, right? That's the question, right? So I want to, so suppose this is 1, right? Or I can also say that the probability that xn does not converging to x is 0, right? So what does that mean? So that is union over all k 1 to infinity. I'll write overall nk 1 to infinity. There exists an n, a n 1 by k complement is 0, right? Both are equivalent, right? Now the question would be, how do you convert this into, right, this, right, or xn minus x greater than epsilon to this? So how do you show this, right? That's the question. Or you have to show that this is, I mean, if this is equal to 1 implies that, xn minus x less than epsilon is 1. So how do you show that? Any idea? Hmm? Any idea? How do you? Anyone?
Sir, just like that, we have did now that modulus of xn minus x is less than epsilon. We constructed from that this
Correct. So
intersection of k is equal to 1 to 1. So
an
just complete.
yeah. So now how do you show that? That's the question, right?
So it is just a complement of the same thing, no, sir?
Correct. That's what we have here, right? So, but
Yeah.
this being 0 does not imply that this being 0 directly, right? So you should show that. Do you agree? Probability of union of intersection and all that does not imply this, right?
Oh, the complete thing, no, sir? Yeah.
Yeah.
This will
Yes.
not imply, yes.
Yes. Right. So, hey, did I write this correctly? Let me just check. Huh? So for every epsilon, there exists an n epsilon such that for every n greater than this is true. Okay. Fine.
Sir, hello, sir.
Yes.
Sir, just you scroll that page, sir. Can you tell what is how do you write from n epsilon to nk, right? Uh, that k terms I didn't quietly understand.
Huh.
Yes, sir.
So
That line.
this epsilon, right? This is true for every epsilon, right? We have it for every epsilon greater than
Yes,
0.
yes, yes,
So
yes.
you give me any epsilon, so I can approximate this by arbitrarily small closer integer, right? So for example, 1 by k, right? Suppose you give epsilon to be 1 by whatever, I don't know. So how do I say? 100,000 root 2, right?
So why you are taking
So
inverse like 1 upon k?
because epsilon is small, right?
Okay, 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 okay.
Yeah, epsilon should tend to 0, right?
Yes, yes.
Yeah, that's why I have chosen 1 by k. Okay, so this is
Okay.
something that you should think about. Maybe you can talk to Savan. Last time I had proved this as well. So essentially, it is based on the fact that you can approximate any real number arbitrarily. So any real number by a rational which is arbitrarily close, right? So that is it. It's based on that. Hmm?
Okay, sir.
Okay. Yeah. So yeah. So now what is it that we have to show? So we have to show that this implies this, right? Let me write that. Okay. So 1 equal
So we
to,
so we essentially made the statement from this statement, like sir, we knew that xn will converge to xn for a very small epsilon, and then we write the
no,
intersection in.
see, this essentially says that this probability equal to 1 implies this, right? Xn converges to x almost surely implies
Yes,
xn
yes.
converges to x in probability. That's what we need to prove. So let's take this. I'll do that. Okay. So intersection over all k, union over all nk equal to 1 to infinity, intersection over all what? This is a n 1 by k, right? So this is n equal to nk to
Nk plus 1 to
infinity,
infinity.
right? So this is what we have,
So nk
right?
plus
Huh? In k plus 1, right? So
A
but
compliments.
no, not complement. I'll just take this one to 1, right? So this I can write. So probability of A intersection B is less than or equal to probability of A, right? How do you prove this?
So
How
by
do you prove it?
addition theorem,
Huh?
we know that probability of A union B is equal to probability of A plus probability of B, negative of probability of A intersection B.
So
From there, if we omit A plus B is also there.
it's easy, right? A intersection B sits inside A, right?
Oh, sir, monotones.
Therefore, one contained in the other, right? So
Yeah,
this
yeah,
is
yeah.
less than or equal to probability of nk equal to 1 to infinity intersection n is equal to nk plus 1 to infinity an 1 by k, right? This is true for every k equal to 1, 2, etc. Right? This is true. But I can change this to equality, right? Why? If probability of something is greater than or equal to 1, it means it's equal to 1 because probability cannot be greater than 1, right?
Yes, sir.
Do you agree?
Yes.
Do you agree? Okay. So now let me call this as B K. Okay. Fine. Or let me call this as B N K. So as Nk increases, what happens to this set? Suppose I take B N K and B N K plus 1. What can you say about these two events?
Sir, B and K will contain B and K plus 1.
Yes.
All right, this is sitting inside this. Okay, this is sitting inside. Okay, do you agree? So that means I can write this as probability of union for all nk equal to 1 to infinity b n k. Now, using these two, what will be the next step?
Sir, continuity will be applied. Limit
A1 is contained in, sorry, A1 contains A2, contains A3, contains and so on. What is probability of union?
So it will be equal to the probability of limit nk 1 to some n.
No, it will be the limit nk going to infinity, probability of
Yes, sir, I'm
bnk,
just doing the
right? Yeah,
Yes.
right? Do you
Yes.
agree?
yes, sir.
Okay, so what is this? This is limit nk going to infinity, right? Probability of what is bnk? Intersection, right? N is equal to nk plus 1 to infinity an 1 by k. Do you agree?
Yes, sir.
Do you agree? Yeah. So if I take nk to infinity, what does this mean? So this essentially is less than probability of intersection. Again, I'll substitute nk for n. Okay, I'm going to take the, well, if you want, I can just take nk plus 1, comma 1 by k. Is this fine? Is this fine?
I think
It is
because
a n k plus 1 comma 1 by k intersection a n k plus 2 comma 1 by k and so on, right? So what I'm
Yes,
doing
sir.
is, this is true for every k. Of course, this is true for every k. Okay. So now, of course, again, this is equality. Why? I'm saying limit of probability is probability. So probability cannot be more than 1. So it will be equality. So now let's look at it in a nice fashion. Okay. So let's call this nk going to infinity. Probability. What is a and k? X nk plus 1 minus x less than 1 by k. Right? Do you agree? This is 1. We are done, right? This is for every k. We are done, right? Why?
It essentially lies within.
Within epsilon, right? You give me any
Yes.
epsilon, there is a case such that 1 over k is smaller than epsilon. So it's true for that also, right? So this limit, right? It doesn't matter. This is for every k. So that is, you give me any epsilon, I can find a case such that 1 by k is smaller than epsilon. So this is true for that k, 1 by k. Therefore, it is true for, this implies limit n tending to infinity, probability of xn minus x less than epsilon is 1 for every epsilon greater than 0. Done. Is this fine? This is a nice proof, right? Do you agree?
Yes, sir.
Yes, sir.
Okay. Okay. Fine. So let's move on. So last class we also looked at the notion of infinitely often, right? So what do you mean by an occurring infinitely often? What do you mean by that?
So it was intersection I equal to 1 to infinity union something like
So
k equal to
one
infinity.
of the things should happen, right? So n equal to 1 to infinity.
Mm.
Sorry, you start from k.
K, yes.
So ak plus 1 of these things should happen, or ak plus 1, ak plus 2, one of these two should happen. So this is from k equal to 1 to 0. If this event happens, we'll say that an occurs infinitely often. Okay? Do you agree?
Yes, sir.
Okay, so let's look at one consequence. Okay, so suppose you have let a1, a2, etc. be events. Okay, so that means it belongs to sigma algebra F. These are events. Let us look at group two cases. Okay, so let's assume I'm doing some sort of a reverse engineering here. So I can have equal to infinity. I can have one of them I leave, one of the results I leave as an exercise less than infinity. Okay. Suppose one of these things can happen, right? So some of the probabilities can be less than infinity or it can be greater than infinity. Okay. So now let's see what are the consequences. Let's look at this maybe. Okay. So I know that probability of union for all I equal to 1 to infinity ai is definitely less than or equal to summation of I equal to 1 to infinity probability of ai, which is less than infinity, right?
Yes.
This is what it says. Now let's look at this less than infinity again. So if this is less than infinity, what can you say about this?
It will go to
This goes
0.
to 0, right? As m goes to infinity, right? If this goes to 0, this also goes to 0. Because this is upper bounded by this goes to 0, therefore the probability should also go to 0, right? Is that fine?
Yes, sir.
So that means it limit m tending to infinity, probability of union I equal to m to infinity ai is 0, right? Is that fine?
Sir, when the summation I equal to m to infinity, then we are taking a limit m tends to infinity. So that is mean from infinity to infinity.
No. You should not interpret it like that, right? So suppose I take m equal to 1, its probability of union over all I ai. That is some number. If you take m equal to 2, its probability of union over all I equal to 2 to infinity. That is some number, and so on. You have a sequence of numbers. I'm talking about the limit of that sequence.
Yes, sir,
Okay.
that I understand. And then when we are taking limit m tends to infinity, so how does it become 0?
How meaning? I didn't understand your question.
So you write that probability of union AI is less than equal to
Sum
summation
of
of probability of
probability.
AI.
That is correct, right? Union bound.
Yeah, yes, a union bound. Then we are replacing I equal to 1 to I equal to m to infinity.
I equal to m to
So
infinity. Yes,
and then m tends to infinity.
correct.
So how does it become 0? I don't know. I am not understanding that part.
Say this is less than or equal to this. Do you agree? For
Yes, sir.
every m. For every m. If
Yes, sir.
a n is less than or equal to bn for every n, if limit bn n going to infinity is 0, this is also true, right?
Yes, sir.
So if this is upper bounded, this should also go down to 0. If it's positive, okay, so this is also greater than 0.
Yes, sir.
Huh? See,
Yes, sir.
you understand, right? So this number, this sequence of number is squeezed between 0 and some other number, sequence of numbers. But that sequence of number is going down to 0. So that will squeeze this or force this sequence to go down to 0, right? It's like this. 0 is here. You have some sequence that's moving like this, okay, to the left, and it will move down. But there is this sequence bn which is to the left. So the moment this moves to the left, this will force this to 0, right? If it is less than or equal to.
Okay, sir.
Basic, basic limits. Okay. Fine. Okay. I can call this as bm. What can you say about bm? b1, b2, b3, and so on.
It's a descending type. B1 contains.
Clear, right? Right?
So it's a reverse, I think.
Hmm?
I think it should be a reverse, no?
Oh yeah, you are right.
Yeah, it's reverse.
Is this fine?
Yes.
Okay. Now, what can you say about limit of this? What do you think about limit of this? This is nothing but
B1, sir.
no. If I call this as bm, what will happen eventually? It's like am, right? So you are taking the union of am till infinity and so on, right?
Simply intersection of all these. Intersection of all B and C. So that limit.
Yeah. So this is nothing but okay. We have to check this intersection. What is this saying?
So probability of happening of AI infinitely often is 0. No.
AI infinitely often with probability 0. This means it does not occur. It does not occur infinitely often. Okay, that's what this says, right? What about this guy? Now we have the other term also, right? What about this guy? So, right. So this proves one part. The other one we haven't. So let me state this as a theorem. This is called Borel-Cantelli. Okay. Let A1, A2, etc. be a sequence, or I'll just say, instead of saying be a sequence of events, I'll say just belongs to F. Okay. Fine. Okay, this is the one thing. Now, first result, if summation I equal to 1 to infinity, probability of AI is less than infinity, implies AI occurring infinitely often with zero probability. Okay, or I'll write it like this: probability of AI occurring infinitely often, I'll call it as AN, infinitely often is 0. Okay, second one, if A1, A2 or etc. are independent, okay, we need independence here. And summation I equal to 1 to infinity, probability of AI is infinity, implies probability of AN occurring infinitely often is 1. Okay? Is that fine? Okay, yeah. So now, if you go back to yesterday's example, A1 was what? A1 is the event that first monkey types Shakespeare. A2 is the probability that the second monkey types types Shakespeare, and so on. So probability of AI is what? Is equal to some probability which is always greater than 0, but this probability was so small, it was 1 over 2 to the something, right? Or 10 to the 30 or something like that. Very, very small probability. But it is non-zero. So the moment this happens, what can you say about this? Infinity, right? And A1 to AN are independent, right? For the monkey typing the typewriter. So this implies probability of AN occurring infinitely often is something. Oh my god, I think I would have lost just 1 second. Sorry guys, I keep getting this issue all the time. Okay, even in the last class I had to face this issue.
So maybe after update it will be okay, because Windows has a lot of very bad updates. So maybe.
Yeah, I have to update. Okay, so you got it right. So the example, the previous example, right?
Yes.
Now
We will
let me.
get one, right?
We will get one.
Yes, okay.
So the next example would be you toss the coin infinitely many times. Okay, I get some sequence, right? Head, tail, head, etc. So the probability. So for example, I'm interested in 3 consecutive heads. Okay, occurring exactly 3 consecutive heads in this sequence. Okay, now A1 is the event that exactly exactly 3 consecutive heads occur. Okay, one set of 3 consecutive heads occur. Okay, so let me rephrase this. Let me rephrase. Okay, so I am interested in let's say, let me simplify it a little. Okay, so I'm going to type again the typewriter. So I'll get a sequence of letters, right? And so on. What is the probability? So if I toss it infinitely many times, for example, I just want this letter to appear. Okay, exactly this, right? So event A1, if I toss, for example, if I start writing infinitely many times, what is the probability that BHARADH occurs infinitely often? What is this? Okay, I want you to think about this and answer. What
So
do you
it
think
will
is the
be
answer?
less than one, because writing a Shakespeare, that event is bigger than writing Bharat correctly. So that event had probability 1. So this should be less than 1.
You are saying something very challenging. The probability is 1, whereas something very trivial is less than 1.
So yes,
Not really, right? So, do you agree?
yes, sir.
Okay. So the way to solve this is, okay, I'll put it this way. I'll take, for example, 20 character, or let's say 20 characters. Okay. This is 1 to 20. Okay. Okay. Now, what is the probability that I observe BHRATH? 1 by 26 power 1, 2, 3, 4, 5, 6, 7. At least this, right? See, Bharat can appear anywhere in 20 characters consecutively, but if you look at a specific, let's say I want this B H A R A T H dot dot dot, very specific. I want
So
this
to
to
the
appear there.
13, right?
Huh?
So these places are fixed. So we are left with 13 places. So to the power
So
13. Yeah.
you could have gotten it in other places also. So the overall probability is more than this, but it is at least 1 by 26 power 7. Do you agree? Hmm? This whole thing could have appeared here, right? I haven't accounted for that. So it also adds up to some probability,
Okay, okay.
right? 1 by 26 power 7 is at least that much, right? And again, the next 20 to 40 I will consider. Keep on dividing this. Now I'll call A1 as the event that this word Bharat appears in the first 20 characters. A2 is the event that it appears in the second 20 characters, and so on. So what is probability of A1 or A2? A1, A2, A3, etc. are independent. So what is the probability of A2? A1, it is at least 1 by 26 power 7, right? Do you agree? So now what can
Yes,
you
sir.
say about this?
So one it should be.
Infinity, right? 1 by
Yeah, yeah,
26 power
infinity. Yeah, yeah,
7.
yeah.
Yeah. And AIs are independent. What can you say? Probability of AI infinitely often is 1. Borel
One.
quantity.
Yes.
So that means Bharat will appear infinitely often, right? If you randomly
Sir,
type.
but sir, but intuitively, how the cases where I am writing a whole Shakespeare and writing Bharat, how can uh, this probabilities be equal? Like,
No, equal in the sense there is a definite chance. That's what it says.
okay, okay, okay.
Okay, the interpretations are different. There, I'm assuming A1 is the event that the first monkey writes Shakespeare. A2 is the event that the second monkey writes Shakespeare, and so on. So, what I'm saying is there are infinitely many monkeys who will end up writing Shakespeare with probability 1. Now, here I'm saying you are randomly typing, for example, or there is only one monkey typing the typewriter randomly. So I'm saying with probability 1, there will be infinitely many BHARATH appearing in that sequence. Okay, that's what it says.
So,
Is that
sir,
fine?
the assumption of this event is independent is just to conclude this summation is infinity, no, sir?
No, 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 no. It's for a
So, what
different reason. You just have to go through the proof of that. Okay. So the proof involves, for example, there is some probability of intersections of these, which you have to write it as product. That's where you need this. Hmm?
okay, sir.
Okay.
Mhm.
Yeah. Is that fine?
Yes, sir.
Okay. Okay, so let's move on. So basically, this is some of these are these were some of the applications of Borel-Cantelli lemma. So let's look at one more one more notion of convergence, which is convergence in distribution. So okay, so we say that Xn converges to X in distribution if You take fxn of x. What is this? What is fxn of x?
So probability of xn less than equal to x.
Yes, CDF, right? You have fx of x. This converges to this as n goes to infinity for all x continuity point of fx of x. Okay, if this happens, we say that xn converges to x in distribution. Okay, fine. Is this fine? Okay, so let me state one more. We say that xn converges to x in mean squared if expected value of xn minus x whole square goes to 0 as n goes to infinity. This is called mean squared error convergence. Now, let's look at a few things. So we have almost sure, or with probability 1. There is with probability, in improbability, there is in distribution, there is mean squared sense, right? Obviously, this implies this, okay? That's something that we saw. But the reverse is not true. It turns out that the convergence in probability implies distribution, okay? This is true. Mean squared error implies this. And therefore, obviously, this also is implied, right? Okay, so this is the diagram that you should keep in mind. So essentially, almost sure implies probability. That is something that we proved. Mean squared error implies probability. That is something that we will prove now. So what is probability? Xn minus x greater than epsilon. This I can write it as xn minus x whole squared greater than epsilon squared. This is less than or equal to, I'll apply Markov. So if mean squared error xn converges to x in mean squared error sense, this goes to 0 as n goes to infinity for every epsilon greater than 0. Therefore, this implies xn converges to x in probability. Okay, so this thing is also done, right? So just to highlight, so we have proved this is done. We have proved this is done. Of course, this is implied because this way. This also is implied because this way. This is the only thing that we haven't proved. Okay, so for example, this thing we haven't proved. Okay, requires proof. So if you prove this, then the other things are well, you know what to do, right? So I want you to prove that xn converges to x in probability implies in distribution. Okay, is that fine? Everyone?
Okay, sir.
Yes.
Yes, sir.
Okay. Okay. So now. So we have seen, we saw what is xn converging to x in distribution. So let's look at, for example, what is known as central limit theorem. Okay, so let's see what is central limit theorem. Okay, CLT for short. Okay, so let's look at one more small thing. So I think one second, what was the notation that I had used? Let me just follow the book. So let me just see what was the notation used for moment generating function. It was gx of r, right? Suppose xn converges to x in distribution. It turns out that this implies phi xn of r, oh sorry, g xn of r of x or converges to gx of r. Okay. If
So you
distribution
yes. So you define MGF by small g. So is it the same capital?
yeah, yeah. Okay. I'll sorry. Okay. So that means if fxn of x converges to fx of x, it turns out that integral, okay, x dfxn of x converges to integral x dfx of x. Okay, this is what it says. Fine. So that means it's an useful tool. If you want to show that a sequence of random variables xn converges to x, you can as well show that the corresponding moment generating functions converge. Okay. So now with this in mind, let's consider the following. So suppose I take the usual stuff, right? 1 over n summation I equal to 1 to n xi. Okay. Now, suppose let's say xi has xi's are IID, okay? IID. Let's also assume that it's zero mean, okay? Well, it's without loss of generality because if the mean is non-zero, I can add a constant to xi and call that new random variable as yi, right? So nothing changes there. Do you agree? Fine. Now, what can you say about probability of Sn less than or equal to, let's say, S? What is this? This is, what is this? This is Fsn of S, right? That is the CDF of Sn. You agree? This is nothing but Fsn of S. Now, as n goes to infinity, this converges to what is the question, right? Okay, I'm going to slightly modify this. Instead of n, I'll have root n, okay? Sn, I'll define it as 1 over root n, not average, okay? So this is the question that we will ask. What is it that it converges to, okay? So now, let's see what is it that, what is the corresponding G Sn of R converges to. So what is this? This is expected value of, I can write it like this, right? E power R Sn. Do you agree? This is nothing but expected value of exponential of R time R by root n summation over all I xi. You agree? This is what I can do, right? So expected value of exponential of sum is the product of exponential, right? I can say product over all I exponential of xi or divided by root n. So now because it's independent, IID, independent and identically distributed, I can say this as expected value of exponential of or x1 divided by root n whole power n. Why is this correct?
Yes, sir.
Because expected value of product is product of expected values when it's independent, right? And identically distributed, it doesn't matter. It should be power n. Okay. So now, what can you say about this expected value of, okay, let's write this e power x, I can write it as Taylor series, right? Have you ever seen this? What is this called?
It's a Taylor polynomial, no? Approximation of ex.
No, it's not approximation. See, I'm saying exact. What is this called?
So what is this star? X star.
X star is some number between 0 to infinity.
So it ends there. The series ends at x star cube by 3 factorial.
Exactly. Why is that? Have you ever seen this kind of a series?
So these kind of approximation kind of
Sir, we use some order functions, sir. Instead of you have written x star.
Okay, I'll give you some intuition. So maybe I don't know if I'll be able to finish this today's class. Okay, so suppose I have a function like this. Okay, this is, let me call this as x, this as b. Okay,
Yes.
now I'll just join this line. Okay, what is the slope of this line? F of b, this is f of x, right? F of b minus f of x divided by b
B
minus
minus
x.
x.
So that means if it is continuous and differentiable, nice function, then there exists a point at which there is the slope of that line is same as the slope, right? Let me call this as x star. So now what can you say? F of b minus f of x divided by b minus x is equal to f of x star. You agree?
yes, sir.
So
Yes, sir.
x star belongs to x and b, right? So I can rearrange and write this as f of x is equal to f of b plus b or minus or plus. See, this will be b minus x and then f of x, f of b minus, okay, or plus x minus b into f of, hey, is this, sorry, it's not, hey, so this slope is not, if it's f dash of x star, right? The slope at this point is f dash of x star, right? Slopes are equal, so f dash of x star. Do you agree?
Yes, sir.
So f of x is f of b plus x minus b into f dash of x star. What is this called?
This is Rolle's theorem, sir.
Huh?
Rolle's theorem.
Okay. Sumit?
Or mean value theorem.
MPT, sir.
Yes.
It is mean
Yes.
value.
Mean value
LMDT.
theorem, right? Now you can apply the same thing for f dash and keep on doing that, you get higher order terms. So if you do it one more time, it will be in terms of x squared. Okay, we'll stop here. If you do it one more time, we'll stop here. Okay. So this is what I have written here. Is that fine?
Yes, sir.
Okay. So now I will write this as 1 plus 1 plus x. So what is x here? Rx1 by root n, right? Rx1 by root n plus x squared is Rx1 squared by n2 plus r squared x1 star squared by 2 n power 3 by 2. Okay, whole power n. Do you agree?
Yes, sir.
Do you agree with this? Okay. Now I have to take. Is there an is there over n? Yeah. Oh, sorry. There is an expectation also here, right? Okay. Fine. So let's assume that. So this is 1 plus expected value of x1 is 0. R squared. I'll call it. This is nothing but variance, right? Let me use sigma squared for that. 2n plus this particular term, right? This I'll write it as order of, okay, r squared. Let's assume that x1 star squared is also expected value of that is also bounded, so it's of the order of n power 3 by 2. Okay, now what happens to this as n goes to infinity? This goes to what? Yes, can somebody tell me?
1.
Hmm?
1.
1. Okay, so let's look at this. What happens to this as n goes to infinity?
E.
Huh?
E.
Is it e?
E power. E power x. No, sir.
Yes, you are right. It's e power
E
x.
power x.
So this goes to exponential of r squared sigma squared by 2. Okay, because n and n cancels and you have r squared sigma squared by 2. So the third term will be n and n power 3 by 2. It will be 1 over n. As n goes to infinity, that goes to 0. Okay, check. This is simple problem in calculus, right? So what is this? This is nothing but the moment generating function of x is Gaussian with 0 mean and variance sigma square. So that means if you look at GSN of R, this goes to GX of R, implies SN goes to Gaussian 0 mean sigma squared in distribution. That means asymptotically, the summation xi over root n looks like Gaussian with 0 mean and variance sigma square. That's what central limit theorem essentially says. Okay, this root n is very critical. Okay, so if you have, for example, instead of root n, if you had n here, okay, if you have if you have n here instead of root n, you would have gotten what happened? You would have gotten n squared here, n and n squared cancels, and you get 1 over n, and as n goes to infinity, you get 0 and you get 1. So essentially, it will be a constant. Okay. So because of the fact that you have taken 1 over root n, it works. Okay. Is this fine? Fine, right?
Yes, sir.
Okay. This is called central limit theorem. So maybe we will continue in the next class. Okay. About the remaining things about central limit theorem. Is this fine? So you know what central limit theorem is. We'll state that very precisely in the next class, and we'll move on to a few other topics and then conclude this chapter. Hopefully tomorrow I'll try to conclude this chapter, and then we will move on to the next chapter.
Okay, sir.
Okay.
It was just an example of central limit theorem, no, sir?
Huh?
You have just
What?
given an example. It was just an example, no, sir?
Which one? No, it's a proof of central limit theorem.
But sir, you mentioned the central limit theorem in such, right?
I
Xn.
didn't say, I am asking this
So how
question.
it gives the normal distribution here, like Gaussian distribution?
What is this? This is what? This is the MGF of what? MGF of Gaussian,
Yes,
right?
sir.
So you can solve this, right? So integral, what is MGF of Gaussian? It's e power rx, e power minus x square by 2 dx by root 2 pi, 2 sigma squared, minus infinity to infinity. This answer will be e power r squared sigma squared by 2. Okay. That is the MGF of Gaussian with 0 mean and sigma squared variance. Okay.
Okay, sir.
Yeah. Yeah.
Sir,
Okay.
X can be any distribution, no, sir?
Okay. X, what is that? X size can be any distribution, IID in this case, with 0 mean and variance sigma squared. Because I'm using expected value of x1 squared as sigma squared, right? So it has to be variance sigma squared.
Sir, even if it is not 0 mean, we can make it 0 mean.
Huh?
Even if X is
Yes,
not
yes,
0
that's the idea. So now if it is not 0 mean, you can just subtract the mean from every xi's to get the same thing, right? So that is clear from here. So for example, you have 1 over a summation xi. If xi is of mean mu, I'll subtract mu. So this goes to Gaussian 0 mean variance sigma squared. Now, what will happen to this? This goes to Gaussian mean mu sigma squared. Oh, sorry, I have to have root n here. It's very important. Okay, remember this root n. Okay, so most people make this mistake of saying 1 by n. 1 by n goes to a constant. Okay, it goes to mean, right? Almost surely it goes to mean. So obviously distribution will be concentrated around the mean and you'll get a Dirac delta, right? Okay. Any questions? Jayant, Nitish, you guys are very quiet. Huh? Fine. Okay. I think there's some issue with your. I can't. There's some issue with your microphone, Nitish. The voice was breaking. Jayant,
Sir?
so are you okay?
Yes, sir. Yes.
Sumit,
Yeah, sir. It's okay,
okay.
sir.
Rishabh,
Yes, sir. Yes, sir.
Sir,
okay.
basically, sir, here, suppose, sir, we have any sequence of the not a finite sequence of the random variables, and we know about their means. Like mean is suppose 0, as you assume there, no, sir. And then all this, by this theorem, we can always say that this action will convert to the Gaussian with 0 mean, sir.
Yes, yes. So essentially, what it means is if you take, for example, some 30 random variables, add them up and divide by root 30 and look at the distribution of that, and that almost looks like Gaussian, which is really cool, right? When you're doing applications, if you get Gaussian, you'll be very happy because it's tractable and all that. So if you have 30 IID, that is good enough for you. 30 is asymptotic for you in practice. So that's why central limit theorem is quite useful.
So,
Okay.
sir, we can also prove its converse also, I think.
What is converse?
Right. Suppose, sir, this xn will going to the Gaussian, this then f of xn will, like, sir, you
Obviously, right? So that is obvious, right? If xn, what do you mean by xn going to in distribution to Gaussian? So f of xn of x goes to fx of x, which is Gaussian, right? So
yes, sir, yeah, directly xn.
there is no converse. I mean, it's trivial, right?
Yes.
It's implied. Okay. Okay. Fine.
Yes, sir.
Okay, I'll stop here and we'll meet again tomorrow. Tomorrow, right? No? No. Next week, right?
Yes, sir. Next week.
Okay, sure. Yeah, thanks. Bye.
Bye.
Bye, sir.